And today we will be looking at the design shear strength of concrete in the beams. Now we have found the different things, different parameters which act together in order to resist the shear in beams. Now it has been found that the design shear strength of concrete, its own capability of resisting the shear, it depends on different various factors. One of them is grade of concrete, the longitudinal reinforcement ratio, the shear span to the depth ratio, the type of aggregate used, the size of beam, the axial force, and the size of the coarse aggregates used. Now this has been through the research of N. Subramanian, and based on an empirical formula that is given by Mr. Rangan in 1972, which considers grade of concrete and longitudinal reinforcement ratio. The IS code has taken cognizance of this and given the values in the table in a tabular form. Now the empirical formula has been developed, and based on this empirical formula the table has been made, and that table has been given to us via clause 40.2 of the code, which says the design shear strength of concrete in beams without shear reinforcement shall be as per this table. Table 19, it has in the first column 100 AS upon BD, and the other columns it has concrete grade. So based on the concrete grade, the different values of tau c in Newton per mm square, the capability of the concrete, its own capability to resist the shear has been given. Now over here on the left hand side we have the percentages. Please note over here the least percentage is 0.15, and if you observe that 3 and above, but at some places it remains the same, we observe it over here. So that's how the values appear. Now suppose there is a beam which has 1% reinforcement and the beam has grade M20, then 100 AS upon BD, that is 1% is here, and M20 is here. So the value is 0.62. So that means if the beam is made of M20 concrete and it has 1% steel, then the value is 0.62 of tau c in Newton per mm square. Now what happens if the value of 100 AS upon BD comes in between, say, these two? Say it comes as 0.90, then what will happen? Suppose the concrete is M20 and we know that this is 0.75, so 0.75 has the value as 0.56 and 1.00 has the value of 0.62. So for 0.90 we will have to interpolate between these two to find the value what is coming in between these two. For that we assume that this is following a straight line. So in between point to point we will assume that there is a straight line, and based on that we will be finding the value. Please note another thing, this 100 AS upon BD, there is a note given over here at the bottom. Now this note says that the term AS which has been used over here is the area of the longitudinal tension reinforcement, the flexural reinforcement, which continues at least one effective depth beyond the section being considered. That means in a particular beam at any particular point, if at all we want to design for shear, in that case at that point we have to check how much steel has been provided in tension. Second thing what we have to check is whether that steel continues for a depth of at least one effective depth. It continues for a length of at least one effective depth. It has to continue further towards the support for a distance of at least one effective depth. Only then that amount of steel will be considered. And there is an exception over here. That exception is at the support where full area of tension reinforcement may be considered. So that has been given over here. So based on 100 AS upon BD and based on the concrete grade, we can find the value of tau c. Now there is also a limit on maximum shear stress. Now what is this limit on maximum shear stress? We know that beyond a certain limit providing shear reinforcement is undesirable. Now let us understand one thing. We always want to do a ductile design. Our designs are such that the steel yields, and because the steel yields, it gives us a warning, it gives us a caution. People and property can be moved to safety. Now over here, suppose the area of steel is provided as shear reinforcement. If we increase the amount of steel over there, if we go on increasing the amount of steel over there, that means due to loading, this steel will not yield because it has not reached its yield point. The steel obviously provided is too much. It has not reached its yield point, so it has not yielded. But there are chances that concrete now would be reaching the yield point, and when the concrete crosses that yield point, we know that concrete being brittle, it will crush. And as it crushes, the web concrete, the core concrete will crush, and without giving a warning, it will collapse. Now, in order to prevent this, what is done is there is a limit put on the maximum stress which the shear reinforcement can take. So because of the maximum stress, we limit the amount of steel which will be coming as shear reinforcement in the beam. So that has been defined over here as tau c max. So defining upper limit on tau c, simply known as tau c max, is necessary, and that has been done in clause 40.2.3. In clause 40.2.3, it is said that under no circumstances, even with shear reinforcement, whatever amount of shear reinforcement provided, shall the nominal shear stress, that is tau v we remember was calculated as Vu upon Bd, the ultimate load upon B into D, shall the nominal stress tau v exceed tau c max. So tau v can never exceed tau c max, the maximum capacity of concrete. Please remember, this is the maximum capacity of concrete, tau c max, and that has been already given in a tabulation form, and that is over here. Consider we have the beam made of M20 concrete. So for M20 concrete, tau c max is 2.8. So we get the value of 2.8. Now as a condition, let us understand one thing. What if there is a beam, it is made of M20, and the value of tau v goes more than tau c max? The value of tau v has gone more than 2.8, say it has come to 2.85. Then we don't have any option, we need to redesign the section. Now when we say redesign the section, what are the different options available with us? In redesigning the section, what I can simply do is, instead of using M20 grade of concrete, I could take M25 grade of concrete. In that case, 2.8 would become increased to 3.1. That means I can design now. There is no problem. So this is one of the options. I can directly take the grade of concrete as M25 and then proceed. Second option, what I can do is, since tau v has got more than tau v has become more than tau c max, how about reducing tau v? We know that the formula of tau v is Vu upon Bd. Vu is the ultimate load. This ultimate load depends on the external load. We don't have any control over the external load. But tau v is Vu upon Bd. We have control over the B and the D. By changing the B and the D, that is by increasing B or increasing D or increasing both of them, obviously if the denominator is increased, the value of tau v would be reduced, and when the value of tau v would be reduced, we can safely look at the value where tau v does not exceed tau c max. So redesigning the section will mean either changing the grade of the concrete or changing the width or the effective depth. Please also note that no sooner the grade of the concrete or the width or the depth is changed, the design will have to be changed right from the first step in flexure, and then complete the design in flexure, and then come to the design of shear. There is another clause which has been given about minimum shear reinforcement. Now we know that in a beam, when shear reinforcement is provided, this shear reinforcement restrains the growth of inclined cracks, restrains or prevents or does not allow it to propagate more. Okay, it controls, they control the growth of inclined cracks within the web portion of the beam. Now the shear reinforcement also provides ductility, and as such it gives us a warning, and the providing the shear reinforcement is of very high importance, because if a beam is subjected to unexpected tensile force due to creep, shrinkage, temperature or differential settlement or sudden overload, and if there is no shear reinforcement, then it could be a disaster. So that's the reason why the IS code says minimum amount of shear reinforcement, even if tau v is less than the value of tau c, its own capability, the external acting load divided by BD, the nominal shear stress, if it is even less than the capability of the beam, the code says provide minimum shear reinforcement. Now what is the clause given over here? The clause given is clause 26.5.1.6. Minimum shear reinforcement in the form of stirrups shall be provided such that ASV upon BSV is greater than or equal to 0.4 upon 0.87 Fy, where ASV is the area of the stirrups, the vertical stirrups, the vertical legs of the stirrups. B is the width of the section. SV is the spacing of the stirrups. 0.4, 0.85 are the numbers. And Fy, look at the parameter Fy. Fy we know is the yield stress, but the code is very clear in saying that it will never be taken greater than 415. So even if we are using FE 500, please note when we are finding the minimum shear reinforcement, the value of Fy will be taken not more than 415. Also, what has been mentioned over here is where the maximum shear stress calculated is less than half the permissible value in the members like lintels, this provision need not be complied with. Okay, so other than that, we have to provide the minimum shear reinforcement. Let us look at another clause which has been given. There is a maximum spacing of shear reinforcement. What is the maximum spacing? Now, maximum spacing between one stirrup to another stirrup. Now, this maximum spacing of the shear reinforcement, the stirrups, is given so that we know that normally the shear acts at around 45 degrees. Principal shear we have understood, so the crack is about 45 degrees. So even if there is a crack, then the crack which is initiated in the beam should be intercepted by at least one stirrup. At least one stirrup. That's exactly the reason why this maximum spacing of shear reinforcement has been given. So maximum spacing of shear reinforcement measured along the axis shall not exceed 0.75 D for vertical stirrups and D for inclined stirrups which are at 45 degrees. Also, there is another condition: the distance between one stirrup to another one shall not be greater than 300 mm. So all these have been given in order to prevent that crack moving ahead without touching the shear reinforcement. At least the crack has to touch one shear reinforcement. Keeping that into mind, this particular clause has been given. So whenever we are providing the shear reinforcement, we have to look at all these categories. First is the shear, finding the shear, then the spacing, the maximum shear stress, the minimum shear reinforcement, and finally the maximum spacing of shear reinforcement.